Hi, everybody. I'm Dinesh Joshi. I'm a senior software engineer and an Apache Cassandra committer.
And I'm Joseph Lynch, and senior software engineer for Netflix, and I'm also a Apache Cassandra committer.
Apache Cassandra is a distributed NoSQL database, and today we'll be presenting a practical way of adding self-healing capabilities to Apache Cassandra rather than switching to a completely new database that promises autonomous operations. So here's today's agenda. We'll be introducing the problem, we'll take you through the goals, and we'll talk about some large-scale operational challenges, present the self-healing architecture, and talk about how we can safely experiment in production and our future work. So running a database is hard. Running a distributed database is even harder due to complexity and exponentially more failure scenarios. It's currently a high-touch activity, which means there is a lot of human intervention. There are new autonomous databases on the market, but it is difficult to migrate to these databases while maintaining 100% uptime and API compatibility. That's why we are proposing adding self-healing capabilities to an existing database such as Cassandra. The goals of a self-healing database are primarily self-preservation, followed by avoiding oscillating states, which means the system does not keep transitioning repeatedly between two states in its goal to self-preserve. System is explainable, which means that an operator can quickly interrogate the system and understand its decision-making rationale. We don't intend to handle all types of failures or magically tune the workload. We can leverage machine learning, but not at the expense of understandability. So, what are the operational challenges that one experiences while running a distributed database like Cassandra? One of them is constantly updating the software, including operating system, kernel, Cassandra itself, runtimes like JVM. We have configuration management that also gets updated from time to time for tuning the cluster for various schemas. We also update the hardware and deal with hardware failures. We also need to collect effective telemetry so that we know what the system is doing and page an on-call engineer if required in the event of failures. Typically, we have two types of maintenances. We classify them as low risk or online maintenance and high risk or also offline maintenance. Low risk maintenance is basically changing any configuration using live control interfaces. Whereas with high risk maintenance, we also update the software or we have to take the instance down for hardware upgrades. This is a higher risk than the online maintenance. If you look at the graph, it models the risk with which the size of the cluster. The larger the cluster, the more risk it entails. Our objective is to minimize this risk. The self-healing architecture is a goal-driven architecture, which makes local and global decisions. It constantly tries to converge to the stated goal via state machines. It does this using two main components. One is specialized agents, and the second is the cluster manager. Here we see the overall architecture. In the middle, we have Cassandra nodes with specialized agents running on each node. Each agent has an internal state machine. It observes the state of the node and reports it to the cluster manager. It is also aware of the node goals and may act to transition the node to that goal state. The cluster manager is a higher level construct that also has its own state machine. It is aware of the world goals and the state of the world. Node agents report to the cluster manager and also get instructions from the cluster manager to transition the cluster to the current world goal. The cluster manager's state machine is higher level than that of the node. And now I'll hand it off to Joey to take you further into the system.
Thank you, Dinesh. So Dinesh has helpfully shown kind of the high-level architecture. Now let's get into the details of how we actually achieve this. And the very first step in the self-healing architecture is the description language for how we describe what we want. And in the paper, we describe this as a hierarchical document config, where for a given cluster of a database, parameterized by environment. So for example, production, test, a particular availability zone, or even a single node, we can set goals for essentially every important aspect of that system. So we typically split those into three parts. We have software goals. These are things like a specific version of an operating system or a database or a configuration of that database or a set of agents or a set of sidecars. We typically refer to that as like a version set or the desired or goal software state. Then we layer that on top of hardware goals, like how much CPU, how much RAM, if we're in a cloud environment, maybe what instance type, how many nodes, the shape and scale of that cluster. And then finally, we provide contextual service level objectives, which are high level goals about the system's operation. These are things like the read latency 99th percentile goal, or how much money we're willing to spend on this cluster, or what are our availability goals. And we're going to use all of these goals to inform the actions of agents. So we can kind of take this goal document and we can compile it down to goals at every level. So for example, in that earlier slide, you saw that we set a P99 latency goal. Well, in order to have a 2 millisecond latency goal at a client, you need to actually compile that down to a goal at every level. So for example, for a 2 millisecond at a client, you might need a 1 millisecond at the database level, which requires your hardware to also meet goals. So for example, your disks have to service IOPS within 200 microseconds in order to achieve a 1 millisecond at the database level. And indeed, we can break these down, these high-level goals down into lower-level goals. For example, we could program a disk supervisor agent to maintain goal state of a given disk latency. And then it might take actions based on that. In the case of a local disk agent, the action that it might take is saying, hey, my hardware is degraded. I need replacement from the cluster manager. But we can actually work this all the way up the stack. So we can, for example, apply this to the Java virtual machine that is running our database. And we can set goals about our runtime to garbage collection throughput. If the database starts garbage collecting more than it is actually running the software, then we know that the database has entered a bad state. And we might desire to, for example, take a core dump for offline analysis, or even to kill the database so that we can recover from a safe state. But it doesn't end at these simple local decision agents. We can also apply the same architecture all the way up the stack. So we can use it to coordinate synchronized backups, where the cluster manager might write into its state store, I desire a consistent snapshot as of time t, and then all the nodes in the cluster will simultaneously try to sync files up to that time, only syncing the deltas. Or for software or hardware replacement, we might have agents which notice that a given node is running the wrong version of software or is on the wrong hardware configuration, and will coordinate through the cluster manager with the rest of the nodes in the cluster to be able to move towards that desired state. And then even finally, we can apply this to very specific database supervisors. So for example, in the case of Cassandra in the paper, we talk about coordinated data repair, which is a process that Cassandra has to run, which ensures eventual consistency of the database. And again, we can apply the same technique there, but this time specifically to the database. And you can kind of see how we can use this architecture to build a library of agents that each solve a particular problem and are experts in their particular domain. But one key aspect of all of these agents is that they're always acting in declarative fashion. And we think that this is kind of core to a self-healing architecture, is that the control plane is never imperative in self-healing. So what I mean by that is that the control plane does not synchronously reach out to nodes to tell them what to do. Instead, the control plane writes intents or goals into a data store. That would be the cluster manager. And then all of the nodes in the cluster are constantly asking, do I have work to do? Is the state of the world different from what I thought? And then the nodes individually plan and act. It turns out that the declarative architectures are much more robust to failure because you have to build them in from the start. Unlike the imperative one, where you can say, oh, I execute this command and I don't even program the case of what happens if that command fails. In the case of the pull-based architecture and the declarative architecture on the right here, we have to build that into the system. So let's see this in action for a couple of common database maintenance activities. First off, let's look at a software upgrade. So an operator might go in and say, I want a new version of my database in production. So they would write this change into the goal document. And then all of the nodes that are running an upgrade state machine would simultaneously note that the desired state and the world state are different. And they would therefore start running an upgrade state machine. And in this case, we know that we have to take nodes down because in order to upgrade the database, we have to safely stop it and then transition to a new software state. So the nodes are going to coordinate through the cluster manager using a locking system. And in the paper, we refer to this as a state machine. And that's because locks are a very simple form of state machine, which really have two states, locked and unlocked. So all of the nodes, half failure zone at a time. So if we have 3 availability zones, we can do maintenance 1/2 zone at a time. We acquire the locks, we stop the database, we then image the machine with a new machine image in the case of a VM, or in the case of a container, a new pod image. And then depending on whether or not that's succeeding, we either boot into the new image or we reboot into the old one and start the database again. And the thing that I want to point out about this state machine, and in fact, all the state machines that are built in self-healing, is failure is built in. There is no option to not program the red path. But the same goes for more complex systems like hardware replacement. So in this case, we are setting a desire for a new shape of hardware, a new disk configuration. And the hardware replacement agent notices that the desired hardware, the goal hardware, is different from the hardware it's running on. And the difference between this state machine and the previous one is that hardware replacement has to start by asking the cluster manager for help, because the old nodes can't just magic hardware out of nowhere. Somebody has to contact a cloud API or has to, maybe talk to operations engineers to actually get new nodes. So the old nodes are going to write a piece of state saying, I'm waiting for a buddy, I'm waiting for a new node, and then they will enter a leaving replacement state machine while new nodes enter the joining replacement state machine. And the state machines for hardware is a little more complicated than software. But the key aspect here is that there's actually a combination of sequential and parallel steps. So in the leaving state machine case, all of your nodes can simultaneously enter the left-hand side of this, right? They can all wait for their buddies. They can all checkpoint state up to your backup store. And they can all enter the advertising state, where they're essentially advertising their data set for replacement. If any of these states fail, we can bring in humans to try to diagnose the problem. But once we enter the dashed part on the right, we actually have to do the same coordination through the cluster manager that we did for the software upgrade, where half a zone at a time, we will stop the database, sync whatever writes have happened since the consistent snapshot, verify the data is the same on both sides, and then finally transfer the token to the new node. The joining state machine looks similar. The difference is that the parallel component is syncing down those offline backups all in parallel, which allows you to keep network bandwidth off of your running nodes and allows you to pull at full line rate. This goes to what Dinesh was talking about with regards to risk. The faster that we can do maintenance, the less time that we're in a mixed mode state, the safer we are. So we prefer to pull at full line rate using the full availability of the hardware in parallel. But then once we start impacting the database downtime, then we have to start doing it 1/2 zone at a time on the right-hand side. And again, it's just the reverse process. We take the deltas, we verify their checksums, and then finally, instead of stopping, we start. So the key insights of the self-healing architecture are that when you're building these agents, you don't do the thing you want to do. Instead, you write down what you want to do. You write it down in a desire store, a database, a configuration, you write it down, and then all of your agents follow distributed state machines to actually achieve that goal. And whenever they need the checkpoint state, they use the cluster manager. And this is really very important because in the self-healing architecture, agents communicate using asynchronous state transitions, not synchronous messages. So in the previous slide, I could have said the new nodes message the old nodes to shut down, but that's not robust because what happens if the message fails? Instead, you communicate through state transitions and state machines. And this is difficult. It's harder for engineers to write, but it's the only way to make systems truly robust because it forces you to program those failure states. Now I'll hand it back over to Nesh to talk about how, once we have the ability to set goals, we can use that to safely experiment on production.
Thank you, Joey. So in order to safely experiment in production, one needs to know that there is no way we can safely experiment in production. So what's the next best thing for this? Much like a science experiment, we make an experimental setup. This is easy using a self-healing architecture where we simply copy the cluster's goal doc to a test environment. The self-healing system restores the cluster state from the backup, and then we alter the configuration of the system to the experimental configuration. Finally, we apply load that is matching the production query distribution while running chaos agents to simulate real-world failures. We then observe logs, metrics for any increased errors or failures. Once this change is verified, we promote the change to production gradually. First, we use the live control interfaces to change a single node, then a whole rack, followed by a data center, and so on and so forth, and all while observing metrics. So, as future work, we can try predicting failures or apply anomaly detection by using state transition history. This is also a general approach that can be used for the systems, especially for specialized agents that are composable. Thank you.